All right, number 3 on the midterm review packet. So we have a car, and it's driving. We're given the initial speed. We're told that it accelerates uniformly. We're given its final speed. We're given a time. We're given a coefficient of friction. Problem wants us to find the acceleration, net force, force of the engine, power delivered by the motor, aka engine, and how far it's going to travel during this time. So, what we know so far at the very beginning is that the mass is 1,280 kilograms. That's of all of the people in the car and the car itself. We know its initial speed is 10 meters per second. We know its final speed is 30 meters per second. And we're told that all of this happens in 5 seconds. And the coefficient of friction is 0.2. Alright, first thing, find the acceleration of the car. Now we have a couple formulas for acceleration. Most important, we already know V initial, V final, and time. So we can use one of the most basic of the kinematic equations. V final is equal to V initial plus acceleration times time to find the value for acceleration. So V final is 30, V initial is 10, acceleration we don't know, time 5. So we go from 10 to 30 in a time of 5 seconds, which means we have a change in speed of 20 meters per second in that 5 seconds, which means that our rate of change is 4 meters per second squared. So every second, our speed is going to increase by 4 meters per second. Okay, that's part A. Already done. Our acceleration is 4. All right, now the second part of the problem wants us to find the net force. So formula for net force is the sum of all the forces, but it is also F equals ma. All right, we know the mass is 1,280, and we just found the acceleration of 4. So 1,280 times 4, 5,120 newtons. That is our net force. And part B. Right now, part C is where things get a little more tricky. So the question wants to know, what force does the engine provide? All right, now we're given this random coefficient of friction. All right, now if you're given a coefficient of friction, it's safe to assume that there is friction in the problem. How do we find friction? That's going to help us because we already know the net force. If we can find the force of friction, then that means that whatever's left over is going to be the force of the engine. So formula for coefficient of friction or force of friction, FFR, is equal to coefficient, that is not coefficient, coefficient times force normal. Now the car is driving on a level surface. So level surface means that force gravity is equal to force normal. So that means force of friction is going to be equal to the coefficient times force of gravity, which is mass times gravity. So that's going to be the coefficient, 0.2, times the mass of 1280, times gravity of 10. Multiply all that together, you're going to get a force of friction of 2,560 newtons. And that's going to be directed backwards. Right now we are told that our net force is 5,120. So basically what that means, the car is delivering some type of force from the engine. Friction is working against the car, and ultimately the car feels 5,120 newtons of force. So we use the sum of all the forces and F net to figure out how to find this. So net force is sum of all the forces, and the only forces that we have, force of the engine and the force of friction. Are they in the same direction? No. So force net is going to be equal to the force of the engine minus the force of friction. 5,120 is equal to force engine minus 2,560. So that means that the force delivered by the engine is going to be 7,680 newtons. Which makes sense. The engine has to deliver a force greater than friction in order to result in a net force of a certain value. Now for part D, how much power is delivered by the car's motor? All right, now power is equal to work over time. All right, now you have a couple options for this because power is equal to work over time, and work is equal to force times distance. Work is also equal to the change in kinetic energy. So I'm actually going to go out of order, and I'm going to do part E first. That'll give us our distance, and then I can go back to D. So how far does the car travel during this time? Well, we know the time. We know V final. We know V initial. We want delta x. So you have a couple options. I am going to totally avoid time and solve it another way. I'm going to say V final is equal to V initial plus 2 times acceleration times delta x. So V final squared is 30. V initial squared 10. Acceleration 4. And delta x we don't know. So 30 squared, 900, minus 100 squared, or minus 10 squared is 100. So it's 800. 800 is equal to 8x. So that means that delta x is equal to 100 meters. Your other option would be to do delta x equals V initial times time plus 1/2 acceleration times time squared. If you do that, you'll end up getting the same answer. All right, so we found the distance. Now we can go up to part D, which wants us to find power. If you wanted to, you could just do work is equal to change in kinetic energy. That will still work out for you fine. But force times distance, since we already have the force, works out a little easier for me. So work over time, which is force times distance over time. And that force is the engine force. So that's 7,680 multiplied by a distance of 100 divided by a time of 5. And you get 153,600 watts as the power, which is not terribly high, but still kind of high. All right, so answers for this practice problem. Part A, 4 meters per second squared. Part B, 5,120 newtons. Part C, 7,680 newtons. Part E, 100 meters. And part D, 153,600 watts.